He has been an influential tech entrepreneur in the LA area for more than 15 years. Prior to joining Core Scientific, he was the co-founder and CTO of Gravity from 2010-2016. Under his leadership, Gravity developed an artificial intelligence and machine learning platform that delivered personalized web content to over 300 million users in real time. Prior to Gravity, he served as the Senior Vice President of Global Technical Operations at MySpace.com from 2003 to 2009, where he led the development of distributed data architecture that allowed the company to scale from just 100,000 to actually 100 million users in less than 3 years. So now he's going to be talking about data is the new business currency. So please give him a big applause and we can start with it.
Thank you. Oh, did I lose my mic? You guys shouldn't applaud until the end. You don't know how well I'm going to do. Well, this talk is about a variety of things, but kind of let me just set my timer. A variety of things, but primarily it is about turning your data into currency, and not turning your data into currency through selling it to third-party providers, and not the standard way of actually turning your data into currency, but actually leveraging the data that you have in such a way that it can help you inform business decisions and help drive your business and help drive your KPIs, whether it be more revenue, greater margins, whatever individual KPI you have at your company. There's a pretty good chance that there's something in the data that will help you make an informed business decision to help drive that KPI that you probably currently aren't looking at right now. And what I've always believed is that data turns into information, which turns into money. And turning information into money is relatively easy. That's why the lines are straight. Turning data into information is actually pretty hard, which is why the lines are squiggly. But I appreciate the introduction, but just real quick, who am I? I've been a serial entrepreneur in the LA area for the last 20 years. I started my career in 1998 at quack.com that went to Netscape. I had a good run at MySpace, then founded Gravity.com in 2009, which is sold to AOL and Verizon. And then I was one of the original actors. I've held a lot of titles, but I'm currently the Chief Data Officer at Core Scientific. And more importantly for this talk is I've always been an avid storage junkie. I know being interested in disk drives is kind of strange, but for whatever reason, I've always been incredibly interested in storage, and I've put a lot of thought into it. I'm a data guy, so I think storage is interesting because it's where data lives. I also, when I'm not computing, I like surfing, golf, and taquitos. So people wanted to talk, wanted me to talk about big data and how data is exploding. And I realized that's not breaking news. I had a breaking news up here. It said, breaking news, big data is exploding. Well, guess what? It's not breaking news. We all know that. We've been hearing it forever. If you look at these stats, 3.5 trillion photos have been taken since the beginning of the camera, 800 billion per year. More data has been created in the last 2 years than in the entire history of the human race. 1 billion people log into Facebook on a daily basis, but less than 0.5% of all data created is ever analyzed and used. Now, those are pretty impressive stats, but that's not the story, because those are from 5 or 6 years ago. That's 2013. It's 2 trillion per year now. And it's less than a year where we create the data. It's 1.5 billion people on Facebook. So the only thing here I think that hasn't increased is we're probably using actually less than 0.5% of all of our data. But the story is not that data is exploding, that 5G is coming, that connected cars, like we all know that already. And we've been hearing it for over a decade. I mean, I don't remember when the term big data was coined, but it was a long time ago. So what's the real story? Like, what is actually worth talking about where we can have a dialogue about something other than the fact that there's just a lot of data being created? Human beings are, data is like a drug for humans. We generate it and we consume it at alarmingly large rates. And I think the real story is not about the massive explosion of data that has set this ball in motion. Again, we've covered that. We all know that. We've all been to plenty of presentations. We all know the facts. People are taking a lot of photos. People are generating a lot of unstructured textual data. I see the real story is that this explosion of data, when combined with 4 very specific new technologies that exist today that didn't exist 2 or 3 years ago, have pushed us into an entirely new paradigm. And it's not the big data paradigm where we just have to scale out more than we normally do, or we've got to scale up. It's a fundamentally different way of looking at data, and for me, it's the first time in my career where I'm actually seeing myself and others look at data from a first principles approach, kind of flipping everything upside down and saying, all right, how are we actually going to look at data? Because we have to now. I mean, we've reached the event horizon a long time ago, and other than just exploding, cloud costs, there needs to be a completely new way to actually look and process data. So if we look at yesterday's data processing pipeline, this is how data has been processed for the last 20 plus, if not longer, years. And I think everybody's familiar with this. You've got your data streaming in, you're collecting it, whether it be your web servers, Kafka, RabbitMQ, doesn't matter, whatever flavor of collectors, you're collecting it on the front end, you're sticking it in a queue probably, but then you're storing it somewhere. You're storing it in a relational database. You're storing it in HBase, Hadoop, Cassandra. You're storing it in one of the many potential places you can store it. And you're storing everything. Then you're selectively processing it. You're running batch jobs. You're doing things that actually are processing the data, not in real time, but you're selectively processing data. Maybe at Gravity we would have 12 hours of Hadoop HBase jobs running each night just to produce data for the next morning. And then that pushes out information. And this is how humans have taught machines how to deal with data for as long as I can remember. But there is a confluence of events and technologies that have been created which are actually fundamentally changing this. And it says tomorrow. I actually think it's today. But I would say today's data pipeline is different. Instead of collect, store, process, we're teaching machines to collect, to immediately process, to selectively store, and then to have a continuous feedback loop ongoing. And it potentially looks like, well, you're just swapping 2 icons. What does this actually mean? Why is this a big deal? Why is this a paradigm shift? And I'll get there. But if you think about it, this is from an architectural perspective, this is a completely different architecture, requires completely different design, completely different way of looking at how you're going to teach your machines to process your data. So why should we do this? Well, the first reason is it actually more closely mimics how the human brain processes data. And we're starting to teach machines to think more and more like the human brain. The human brain, as of right now, you are in real time collecting data. You're processing what I'm saying in real time. You're selectively storing certain things I'm saying. You're ejecting other things that I'm saying. And you're going to have a recurring feedback loop that's going on in real time. That's how the human brain works. This is how the human brain processes data, which actually looks pretty close to our new data processing paradigm that we're seeing come out these days, where the brain collects data, it processes it, it selectively stores it, and it produces information. Which is very similar to this pipeline. So if the academic aspect of why we should implement this because it's like the human brain isn't a good enough reason, the other reason is because of money. Because you're going to make more money if you run a data processing pipeline like this. And historically, we would rely on processing subsets of data, or we would process data in a degraded fashion. And what does that mean? I'll give you an example. So this is one of hundreds of different algorithms that we had back in the day at Gravity. And what we did is we actually had 2 pipelines. We had a real-time pipeline and we had a batch processing pipeline. In the real-time pipeline, we weren't able to use a lot of the techniques that and open source products that are available today. We had to build it ourselves. And it was almost secondary to our batch processing pipeline. But our real-time algorithm would be able to tell what a user had been doing 10 minutes ago, which actually gave context. And it would perform at, this one individual one that I just pulled performed around 95% if we were running a real-time algorithm. With our batch processing algorithm, where at night it would churn through all of the data, 10, 12 hours, and that would be then set for you for the day, our accuracy would drop by 10, 15%. And when you're powering the homepage of the Wall Street Journal, 10, 11% is a significant amount of money. The problem is we couldn't use our real-time algorithm the vast majority of the time, because when we batch process data, we were able to deliver content to users, not ads, but personalized articles to users in under 200 milliseconds because it was already there. It had been batch processed and it was just sitting there in cache waiting to be delivered. When we were doing stuff in real time, it would take up to 2 seconds. And we couldn't hold up the homepage of the Wall Street Journal or the Huffington Post or any of our partners for 2 seconds. So we rarely got to use this one. And it was just because the technology 8, 9 years ago just wasn't there. But it's there today. And that's what makes me excited, because we would have loved to have been able to leverage this new paradigm back in the Gravity days. So why now is the next question I would ask. Big data has been around for 10 years. What is happening that's making this change today? I mean, yeah, the global footprint of data has been exploding for a while, and we reached the event horizon of our inability to process all the data we have. Everybody collects data because they feel like it's really useful. Nobody really does much with it. But today, there's 4 independent technical advances that have occurred, somewhat semi-independent technical advances that have occurred that have been able to push big data processing to an entirely new levels with an entirely new paradigm, like we spoke about earlier. So what has changed? We've got the perfect storm happening right now. We have huge advancements in GPU architecture. The GPUs of today are not like the GPUs of even 3 years ago. And I'll cover all these a little bit deeper. We've got advancements in AI, particularly deep learning neural networks that have completely changed everything in just the last 3 or 4 years. We're seeing a significant amount of capital investment from both private companies, public companies, venture capitalists, private equity companies, investing in GPU-centric software companies. Companies that virtually every open source software that you know of, from the entire Apache Commons project, somewhere there is a group of people rewriting it to run on GPUs 10 times, 100 times, 1,000 times faster. And there's a significant amount of money being funded to have the software stack for GPUs in order to make the GPU the next CPU. And the fourth is the supporting infrastructure around the GPU. So all the data centers we see today are built with one thing at the core. The core is the CPU. The GPU has completely different requirements than a CPU. And when I'm talking about supporting infrastructure, I'm not talking about faster DDR or the small things. I'm talking about entire companies that have built high-speed SAN storage just to feed data into the GPU. At Core Scientific, we build our own proprietary, designed from the ground up data centers on greenfields that are GPU-centric, and they're focused purely on all of the difficult problems that GPUs have that you don't see from CPUs. So supporting infrastructure is not a faster DDR chip. It's the supporting infrastructure is massive and it's necessary. So first, let's look at the GPU architecture. So what's changed? Okay, so all GPUs have never been equal, just like all CPUs have never been equal. But today, the term GPU is used interchangeably to describe what I would say are kind of 2 different things. NVIDIA has actually now separated their product lines. They've got the gaming GPU and their enterprise GPU. So what's the difference between these two, other than the fact that this costs $700 and this costs $10,000? That's a whole other discussion, but you've got tensor cores, you've got a whole range of things that are tailored towards HPC, analytics, AI, data processing, when over here you've got things that are looking at shadows and like ray tracing and things that are good for graphics. So they've completely separated the two of them, the two individual product lines. And this is just an example of this. Actually, this P200 is actually higher up than the gaming one that I showed previously. But you can just see kind of the performance, and you definitely get what you pay for. Now, if you take a GV100 and you plug it into your Oculus, it's not going to make your Oculus Rift work any faster, because that's not what they're designed for. But if you're training an AI model, you're training a deep learning neural network, you're going to get significantly higher performance from your enterprise NVIDIA GPUs than you are from your standard gaming GPUs. And there's more CUDA cores. There's a whole other range, but that's kind of not. That's kind of a different topic. But in general, GPUs are not just for gaming anymore. So if you think about it, what have GPUs done? So it took 3 hours using GPUs for scientists to crack the genetic code behind a deadly strain of E. coli, which saved a lot of lives. In 3 minutes now, it takes oncologists using GPUs can observe the results of radiation on a tumor in 3 minutes through GPU processing. There's 125x extra performance on a GPU-based computer versus a CPU-based computer when the scientists studying the Big Bang moved from CPUs to GPUs. So this is a paradigm shift and a revolution that it's still nascent, but it's here to stay. It's coming. And obviously, it's already being used in a variety of different industries and verticals. So the next thing powering the paradigm shift is advancements in AI. So it's somewhat tangential, but I think it's really interesting to think a little bit abstract about why AI is a key driver of this data shift. And it's perfect that it's one of the drivers of this data shift. And the reason is because as we're teaching machines to think more like humans, AI has virtually every AI model or type of model has been, for better lack of word, modeled after nature. And you can look at things as, decision trees are actually modeled after real life trees. Random forests are just thousands of decision trees modeled after a forest. Neural network is modeled after the human brain. Genetic algorithms are modeled after how they're modeled after DNA splitting incorrectly. And deep learning is effectively just a more advanced version of multi-layer neural networks. And I would go so far to argue that SVMs are ways of a natural expansion of how we measure things in our own three-dimensional space. Effectively, AI, there's very few AI techniques that have some basis in modeling nature. Because if you think about it, nature is the greatest AI out there. But most importantly for this paradigm shift is deep learning. So deep learning over the last 3 or 4, so neural networks have been around for a long time. I've always been personally very interested in them. But they've never really been used successfully until the last 3 or 4 years. And the term deep learning is effectively just a way to, this is an understatement, but initially, it's expanded, but initially it's just a way to have a multi-layer neural network and a variety of different techniques that enable neural networks to operate in ways that they haven't been able to before. And now for a lot of different problems, they are considered the best-in-class solution. And coincidentally, which is just random, they weren't necessarily designed to do this, but DDNs have a very uniform structure that fits incredibly well into the parallel processing aspects of these new enterprise GPUs. So you already have a pretty strong customer for this new level of GPU. So the third is capital investment in GPU software. So this is the list of companies that are currently working to redesign either their entire or parts of their infrastructure to support GPUs and GPU acceleration. Some of these have not actually crossed that finish line yet, but in every single one of these verticals, vast majority of these companies have funding and are currently working to move things over to GPUs from CPUs, or at least you've got disruptors in all of these industries that are taking pre-existing code, whether it be a Postgres database, whether it be Spark, whether it be MySQL, I mean, anything you can think of. There are teams of people rewriting them to run incredibly fast on GPUs, which enables us to exit the batch processing world and actually enter into the real-time processing world at scale. We've been able to real-time process data before, but again, we process 0.5% of the data we collect, but the ability for us to process 100% of that data in real time is coming, and it's going to revolutionize everything, in my opinion. So the fourth, and what I would argue the most important part of the equation, is supporting infrastructure. And the question is, like, what does that mean? And we take that for granted. The reason we take that for granted is because every data center that we've walked into over the last 20 years has been built from a CPU-centric mentality. Everything is built around the CPU. So we're just used to these things already existing. We're like raised floors and HVAC don't impress us anymore. Hot, cold aisles, all those techniques, all those things that we just know after running large-scale CPU farms, you got to completely throw out the window when you're talking about GPUs. GPUs are fundamentally different. They're different machines. They have got completely different needs. And you have to have completely different supporting infrastructure from the ground up in order to run GPUs at large scale. If you're going to scale out, a 10,000, you can scale out a 10,000 server, web farm on Amazon with a few clicks. But if you're going to try to do that with GPUs, you need to do, it's nascent enough right now that there needs to be a lot of work actually to do it. So why is it necessary? Well, it's an iceberg problem. And we're only looking at the tip of it right now. But GPUs currently face a major roadblock in achieving their full potential. A very small subset of the GPUs in the world today have ever hit 100% compute. Compute power is increasing significantly faster than the size of the onboard VRAM, the size of the onboard memory. And that is a big problem, because the ability to keep entire data sets in GPU memory becomes increasingly difficult as our overall global data footprint grows. As your data footprint at your company grows, the cost of keeping all of that data in the VRAM of the GPU is currently something that is cost prohibitive. And when a data set isn't in GPU memory, being able to, having the GPU go out and retrieve it from somewhere else is an incredibly expensive call. It's a call that is best case is going to cause massive latency in your application. Worst case, your application is just not going to work, because GPUs are able to hit VRAM and compute and process data so fast and they're so data hungry. The goal is to just push as much data into the GPU as fast as you possibly can, because you want the GPU to be, it never will be, but you want the GPU to actually be your bottleneck. You want to sit and say, we need to add more GPUs because we've maximized compute, which nobody does. People add more GPUs because they have too much cold data and they need more VRAM. But you'll have GPUs on Amazon running 5-10% compute, but things are running slow, and it's because they're paging to block storage. As they're paging out to block storage or even Amazon SSD, the speed to actually pull that data into the cold data into the GPU is so high that what they do is people go out and they buy more GPUs just to increase your overall cache. If you think about it, that's incredibly expensive cache. $10,000 a pop. There's probably cheaper ways to cache data. And the current infrastructure that's been designed to support CPUs don't need this data. CPUs have a variety of different caches. There's not really an issue of trying to feed data into the CPU. So that historically there haven't been a lot of companies or efforts to be able to push this much data at this high speeds, because it wasn't necessary before. You would sample your data. So as we are looking to solve even just the top of this iceberg problem, there's two real goals with GPUs and the supporting infrastructure of GPUs. The first thing is you move data into the GPU as fast as you possibly can at all costs. And you can do that through things like NVLink, NVSwitch. They're created by NVIDIA, but they're open source products. And what they do is they enable you to not necessarily bypass, but have a faster route through the PCI bus, so two GPUs can talk to each other and share memory with each other. It's still expensive. It's still 4 copies each way, but it's a lot faster than just going off of through the PCI bus. The next thing you need, and some companies like Cisco and Dell have actually taken NVLink to the motherboard, which allows the GPU to access host memory, which I think is going to be a massive change in everything, where if you can actually augment GPU memory with host memory, then that changes a lot of things. You also need incredibly fast networking fabric, and you need incredibly fast storage. Then goal number 2 is keep compute at maximum performance. Most GPUs will actually, unless you actually get really under the covers, you don't even notice this, they'll throttle themselves when they overheat. You see a DGX1, DGX2 will actually self-throttle if they get too hot. So there's a lot of unique computational fluid dynamic techniques and static airflow, and not just the standard raised floors, hot cold dial techniques that are required when you're running large-scale GPU farms in order to not have them rate limit their compute. You also need extremely high density data centers. GPUs draw a significant amount of power, much more power than the average CPU. For example, at Core Scientific, we custom build data centers for GPUs. We don't even look at a facility that your average data center is 5 to 10 megawatts. We won't even look at building on a plot of land unless it has access to 50 plus megawatts of power. And we've got about around 600 to 700 megawatts of power locked up in the United States. And I think that's somewhere between like 1/3 or 1/4 of Amazon's entire footprint. And we're dedicating it completely towards GPUs because we see this revolution coming. And then you need, and we have at Core, proprietary monitoring and tuning applications. The standard apps that, back in 2005, you'd go out, you'd buy 10,000 Dell servers, you'd get a free, piece of software, I forget what it's called now, but you get it with HP, any of them, where you could monitor thousands and thousands of servers from one central terminal. GPUs are somewhat still nascent. There's some software packages out there, but you kind of have to roll your own at this point. So, of those 4 things that have created this paradigm shift, and of the things that you actually want to do and what you're trying to focus on when you're trying to solve for the problems that GPUs face, how do we do it at Core Scientific? So there's something called the AI Ready Reference Design, which was started by NVIDIA. It makes things a lot easier because it's kind of like you can install Zookeeper, Hadoop, HBase, HDFS, I don't even know the rest of the list yourself, or you can just go to Cloudera and they have it all packaged and bundled for you. And that's kind of what NVIDIA has done here. They've created a reference design with a lot of different vendors, and they've kind of sent it out into the world. So what we do is, at Core, we custom design data centers from the ground up to support GPUs. We're building GPU-centric data centers, of which I don't know if there are any others actually in the world right now. We've partnered with Pure Storage. In order to, like I said before, once your data set is outside of the overall memory that you have in your VRAM, in your GPUs, you need to get data from somewhere else into the GPU as fast as you freaking possibly can. And to do that, you have to do it with some of the fastest disks you can get out there. And we're working now directly with Pure Storage in order to do that. You also need the fastest network fabric that you can possibly buy, because to get data from Pure to the DGX or to the Cisco or to the host machine that the GPUs live in, you don't want your network fabric to be any type of bottleneck. It's always going to be one of the slower parts, but you want to minimize that as much as possible. So we use Arista, but there's a variety of different ARI-ready or ARI-approved network fabrics. So why did we go with Pure? I used to think all SSD was the same. I hate to admit it, when I was at MySpace, I was good friends and consulted with a couple of VCs that I just knew up in the Valley, and they'd call me and they'd say, what do you think about this technology? What do you think about this technology? And I would tell them, like, oh, we're using this, we're not using this. And I remember one of them, whose name I won't mention, was asked me about SSDs. And in 2006, I said, what are you talking about? You should not invest in SSD disk. So, I mean, that shows you it's very easy to be wrong on a lot of things. But I've bought probably, for better or worse, I don't know if this is something to be proud of, but I've bought at least 10 plus different pieces of storage from 10 different storage vendors through whether it be fiber channel, Ethernet, NAS, InfiniBand. Just over the years, I've gone through a ton of different types of storage. So I was wrong. All SSDs are not the same. And the example is that the SSD drives in the internal drives on a DGX1, which you'd think the internal drives obviously are directly connected to the bus, would be the fastest you could get. They can push 6 to 8 gigabits sustained into the GPUs on a DGX1. Pure storage in an ARI-ready design with a fast network fabric and with a data center that has been built to power GPUs can push 75 gigabits per second throughput into the GPU. And that is a massive difference. And it's not just because it makes things faster. Finally, though, Pure is truly horizontally scalable. Everybody says they're horizontally scalable. I remember like Oracle 10, you're supposed to be able to plug in the Oracle Grid, 10 years ago. People have been horizontally scalable forever. Pure actually is truly horizontally scalable. And the key thing here is that the difference doesn't just enable faster workload processing. So if you're running a query and you've got a 2-second, your query takes 2 seconds. You do all this work and now your query takes half a second. Okay, that's nice, but does it really matter that much? I guess if you're running a lot of queries, it probably would. But in general, the difference is that the new ARI infrastructure doesn't just make things faster. It enables customers and companies to process data workloads that were too large for them to ever process before. Remember that 0.5% stat? This paradigm shift in how we look at data is going to take that stat to, I hope, at least double digits. And what that enables companies to do is to start out visibility into data that they never had visibility into before, which directly drives, when that data is turned into information, that directly drives your KPI decisions. It gives you information on decisions for your business that you did not have before. And you can see direct correlations to it. I'll show you some. So we had a customer who's heavily reliant on Omniside. I'm not sure I think they're here actually. It's a pretty amazing GPU-based, GPU-accelerated database / visualization technology. There's really not a lot out there like it. They were running it in AWS. Their entire infrastructure, they had a 7-figure bill in AWS monthly. We went to them and we said, keep all your compute in AWS, move your GPU or your CPU compute and storage in AWS, but move all your GPU-centric stuff over to us. So we migrated them from 14 AWS GPUs to 2 GB100 GPUs in a DGX1, backed by Pure Storage in a custom core GPU data center with an incredibly fast network fabric. So they went from 14 GPUs to 2 GPUs, and they received a 400% performance increase immediately out the gate. From 14 to 2 with a 400% performance increase. And that was utilizing DGX's internal SSDs. We then plugged them into Pure, and when we plugged them into Pure, the performance boost increased to 800% after taking the Omniside database, moving it outside of the local SSDs, putting it on an external NAS, which is counterintuitive. We then had an 800% increase in speed. Now, initially, this was a huge win because their 2-second queries were taking half a second. And for people who are the 10 data scientists who are sitting in Omniside on a daily basis, that made them very happy. But it quickly turned into the data team over there, their company realizing, wait a second, we can now load all of our data into Omniside. We can load billions of rows, we can have billion row tables, not just hundreds of millions of row tables. And then once that happened, it became spread out and it became a de facto tool for not just a small group of the data scientists, it became a de facto tool for hundreds of people in the company. It's now how they measure all of their KPIs. And they load huge amounts of data in, which they were never able to load before, and it's actually informing the business decisions that the CEO is making because he now has visibility into things he had never had visibility into. Because you can't, all the data they have was just going up to S3, and they were looking at small segments of it. And as they start to look at more and more and more of it, they're starting to actually derive more and more information, which directly informs your business decisions, which directly correlates with revenue or margins or whatever KPI you're actually trying to optimize for. And it also sped everything up. So I think I've got like 5 minutes left. I want to give people a chance to ask questions, but I also want to talk about this. Today we're actually announcing a partnership with Fast Data. So Fast Data is GPU accelerated Spark. It is, they've rewritten Spark from the ground up to run, I'd say 90 to 95% of the code actually runs on the GPU. Small subsets offloaded to CPUs, but it runs at least 100x faster. We've seen even greater performance. And the stack is, we've got a core scientific intelligent infrastructure, our data centers. We also have a proprietary control plane on the software side. We power with NVIDIA DGX1s and DGX2s. We layer pure storage on top. Arista sits in here as well. And then GPU accelerated Spark, Fast Data sits on top of the entire stack. And what we're offering now is we're offering free POCs for, I think, the first 5 people who want to apply of real data. We're direct connected to Amazon. So if you've got your data anywhere in Amazon or Azure, we can move it through private dark fiber that we've lit up. And you can take your Spark jobs and see what your Spark jobs are like today and test them with production data or development data and test your Spark jobs in an RE environment and truly see what the 100x acceleration without having to rewrite any code actually feels like. It's pretty amazing. To do that, email sales@corescientific.com. So thanks, and I want to give time for some questions. All the way in the back. When is it coming?
Sure, but maybe more granular than that.
Well, if you think about kind of the 4 drivers, so deep learning is still in a nascent field. AI itself, I mean, if you turn the TV on, you see AI everywhere, but AI is still nascent. So one of the primary drivers of GPU consumption is artificial intelligence, and that's still kind of, if you ask people, do you want to use AI at your company, they say yes, and you say, what do you want to do? And they say, we don't know, we just want to use AI. But as that field becomes less and less nascent, that is going to continue to push it. And then also you've got companies like Omniside. There's a lot of HPC analytics companies that are, again, like I said, Postgres, Spark. They're not really AI. They're components of usually AI pipelines that are currently using GPUs and driving that consumption. And then also you've got NVIDIA making a big push. Like they're selling the DGXs, but they're actually open sourcing the DGXs. And Cisco's got their own version. Dell's got their own version. So you're starting to see traction from the supply side, which I would think is indicative of increasing demand on the demand side.
So I think we have one additional question, and the last one will be the person on the back before we just.
Sorry,
okay.
So, did you receive any pushback from the industry when you wanted to do GPU-centric data centers for your storage?
Not really. I mean, the industry we received pushback from was the energy industry.
Really?
It is surprisingly hard to go. You can't just go to a nuclear power plant and say, I want 50 megawatts, because they don't believe that you're going to use it. They'll give you 5, and then you have to prove that you'll use 5, and then go to 10. And it took a while, actually, until our new CEO came on board. He was able to really drive that. But for a while, we were having pushback from the energy industry trying to actually get our hands on that much power. But that's, if I was thinking the pushback, that was the hurdle, actually.
So we do have one last question there,
Sure.
and then we're going to break up for lunch.
Great.
So,
Where do you see quantum computing playing a role within this space, and what sort of runway do you see that happening? In other words, when do you see quantum
That's a great question.
kick in into what you just talked about?
Okay, so the current one of the current issues with quantum computing is similar to neural networks actually, where you'll put an equation or a question into a quantum computer, similar to a neural network, and you get spit out an answer, and you don't know why. There's no proof. Neural networks face that problem. If you have a random forest, even an SVM, you can actually see, okay, how did it come up with this? And right now, with the kind of the best-in-class quantum computers, they're limited to a very, very small select set of problems. So I do see that quantum computing is going to make all of this irrelevant. The question is when, and it's still, yeah. The question is, I think, well, it's people think like quantum computers are 100. You get a quantum computer for $8 or $9 million, which I mean is not cheap, but it's not out of the realm of a large enterprise. The problem is that the problems that they can solve, the solutions that they can derive, are only fit of such a small problem set. It needs to have a larger problem set to be able to actually, I think, get mass consumption. I'd say, I mean, I'm just arbitrarily throwing numbers out, but I don't see anything for at least 5+ years probably, if not 10.
Okay, so there's actually one additional question. And we're
Sure.
done, I promise.
So
I've got plenty of time, no big deal.
in respect to, I know how much, 50 megawatts, insane amount of power. The investment, not only in that, but with the graphics cards that you are, GPUs that you're investing in, 10,000 a pop. Do you actually see a return on investment before the next NVIDIA, or the life cycle of that ends? Because obviously, we've reached 7 nanometers, and after that, I don't know what they're going to. I guess Moore's law has reached its
Yeah,
end, but
no, that's a good.
are you guys able to profit from all of that investment in time before the next generation comes? Because the cycle of hardware is just accelerating really quickly.
No, and that's a great question. And so first to address like 7 nanometers, I don't want to say we've reached 7 nanometers. We've had like a couple successful tape outs that people were talking about, but even TSMC, one of the foundries, has actually gone back to 10 or I think 12 nanometers. So, and with the amount of R&D that NVIDIA has put in, billions of dollars and years of R&D into these specific chips, with not chips, but these systems that have tensor cores, which are still not even fully utilized. I think you're not going to see a huge leap from the current hardware today until it all starts to get properly utilized, and it will as you start to see this list of software companies. But it's only I think I just heard it was maybe a couple weeks ago that TensorFlow actually started utilizing tensor cores. You were still running CUDA. TensorFlow was actually, your LSTMs on TensorFlow were actually being using CUDA instead of a tensor core. So the hardware itself is so far ahead of the time that I don't see us going through 2 or 3 year. There's going to be incremental cycles, but I don't see any real major changes over the next few years because the software to actually utilize it is still catching up. But that's a very good question.
Well, thank you very much.
Thanks.
Okay.